everyone, my name is Lou Del Monte and welcome to Del Monte on Science. Today we're going to discuss the mysterious nature of light. And most of the material I cover is in my new book, Unraveling the Universe's Mysteries, available at Amazon and at Barnes & Noble online. So you might ask, what's so mysterious about light? Most people don't think light is mysterious. As a matter of fact, if you enter a dark room, that feels mysterious, and the first thing you do is you turn on the light. And so light seems to be a welcome addition to mystery. However, from a scientific viewpoint, light is mysterious, and we'll discuss that. The first thing is that light exhibits two properties, and one is that it exhibits the properties of a wave, and it exhibits the properties of a particle. For most of the 19th century and the early part of the 20th century, science considered light a wave. But they had a problem, and that is that they could not explain with that model of light, they could not explain something called black body radiation. Now, what is black body radiation? Well, black body radiation, and this refers to the photoelectric effect. If you have a perfect black body, a surface, and light impinges on that surface, it will absorb that light, and if you heat up a perfect black body to a certain temperature, it gives off all frequencies of light. That's a perfect black body. Now, in your home, you have an example of a black body when we talk about a light bulb. A light bulb is, for all intent and purposes, a black body, because what you're doing is you're heating up the filament, and it's emitting light in all directions, okay, around that filament. So that's an example of a black body. And with the wave property of light, up until the entire 1900s and the early part of the 20th century, they could not explain why a certain property of a black body that via the wave theory. And what was that property? Well, basically it went like this. Here's your black body, okay, and they found that if you shined light, if you shine light on this black body, so you put light on it, so this is light, off came electrons, okay, and so that it makes sense that light was energy and off came electrons. But what didn't make sense was that if you shined light, it was the intensity. If you shined low intensity light, if the intensity of light was low, you got few electrons coming off. If you shined high intensity light, you got more electrons. But the strange phenomena was that the energy of the electrons was the same. So high intensity light gave you fewer electrons, rather low intensity light gave you fewer electrons, high intensity light gave you more electrons, but the energy of the electrons was the same. The only way that they could actually get higher energy electrons was to increase the frequency of light. So they had to increase the frequency, and then they'd get electrons with higher energy. So that's the conundrum that they were facing. Why is this? The wave theory of light did not explain that. And we should discuss just briefly what we mean by frequency of light. Now, it turns out that if we go to your light bulb in your house, there's the light bulb. Okay, it's plugged in. Here's the filament and all that, and it's giving off light. You only see, the light that you see is only 10% of the light that is being given off. That most of the light is in the invisible range, and that's related to the frequency of the light. Now, frequency has to do with, and the analogy would be thinking about you're at the seashore, okay, and here's the seashore, here you are, and you're watching waves come in, okay. If you count the number of waves over a certain period of time, the number of waves divided by the time is the frequency, okay. And that's the same thing with light. If you look at the frequency, a low frequency would be like this, and a high frequency would be like this. Okay, so the frequency is actually a measure of the energy of the light. Now, in 1900, this is an important date, 1900, Max Planck hypothesizes that the energy that's given off, the energy of the electron, is related, it's a function of the temperature of the black body. So he hypothesizes the temperature, which is again a form of energy, is related to the energy of the electron. And that when a black body is at a given temperature, it emits a quantum of light. So he's actually saying that if you raise a black body to a given temperature, you actually get a quantum of light. And that was revolutionary in its time. Now, an interesting thing is that the whole concept that light is quantized went against conventional wisdom. Everybody said light was a wave. And Max Planck comes along and says, well, it looks like it's quantized. And so they confront him with that. Are you saying light is quantized? And he says, no, my theory really is just a generalization. It doesn't apply over the entire range. He discounts his own theory, all right? So he sort of backs away from it, in effect. Although we're getting closer to the reality. The wave concept of light would have prevailed had it not been for Albert Einstein in 1905. He takes Planck's information and says that, in effect, that it took a certain quantum of light Now, to a quantum with a specific energy to give off an electron with a specific energy. So what he's saying is that it was the energy of the quantum of light that was related to the specific energy of the electrons given off. And that if you shined more, if you just increase the intensity of light, shining more light of the same level of energy, you just get more electrons of the same level of energy. And Einstein says, okay, basically the quantum of light with a specific energy gives me an electron with specific energy. And this becomes the beginning of quantum mechanics. In the next post, we're going to look at the second mysterious aspect of light, which turns out to be extremely important because it becomes the pillar of special relativity. Thank you.